What is up, amigos? Today we are looking at inviscid flows versus viscous flows. So what we're going to go through, what is an inviscid flow, what is a viscous flow, and when is a flow inviscid or viscous, and this comes down to two main parameters, the Reynolds number and the flow separation. So what is an inviscid flow? So we've heard this term quite a lot, viscosity and viscid flow, viscous flows, but there are a few different ideas that we need to cover in order to understand what an inviscid flow is. So let's say we have a regular flow just coming along, has a free stream velocity of u infinity. Now, in real life, there are very little few flows that are actually inviscid. But an inviscid flow means that it has no viscosity, as you'd expect, so no friction between particles. So let's say you have a few different particles all dotted around. And if you've seen our video on boundary layers, you'll understand what I'm going through here a little bit more. If you haven't, you can check it out in our playlist. So you have all these different little particles around and they're all moving around. And because they're so close to each other, they each have an effect on each other where they're trying to pull each other in a different direction. So for example, this particle here is moving to the top right. So this is going to try to pull this particle in the same kind of direction and this particle as well, because they're all kind of touching, they're all around each other. And likewise, this particle in the top left is going to be going up in the top, a little bit less right, but still top right. And that's also going to try to pull different particles around with it. So there are going to be these reaction forces. So an inviscid flow means that there's no friction. So this does not happen. So all these little particles around, they're not actually interacting with each other in terms of friction. They're not trying to pull each other in different directions. That's one point that we need for there to be an inviscid flow. What's more, there are two other parameters which we often don't consider, and this is for a very good reason, and we'll talk about it in a second. The second one is that there's no thermal conduction. So this means that there is no change in temperature between different particles. The third one is that there's no diffusion. So diffusion in general is when you have one parameter. So this could be heat, it could be mass, it could be whatever. And this moves through a system. So let's say we have a box and we have all these, over here we have all these particles all dotted around and we have a high mass. So mass is very high. Over here we have few particles and the mass is very low. No diffusion means that these particles are not going to be moving into this part and transporting mass with them. So there's no diffusion. So why don't we really consider no thermal conduction and no diffusion, generally speaking, when we talk about an inviscid flow? The reason why is because of the term. So the term inviscid, we often just associate typically with viscosity, and that just reminds us of friction. So whenever we say no inviscid flow, or when there's an inviscid flow, we think, okay, there's just no friction. But it also means that there's no thermal conduction, but also no diffusion. These are two very important parameters, but it's important to remember these two. Now, what is a viscous flow? It's pretty much the opposite. So we now do have friction, which means that if we have this system again coming back, these particles are now interacting with each other and they're trying to pull each other in different directions. There's friction between them. We do have thermal conduction, so there is now changes in temperatures across systems. And we also have diffusion now. So there is mass being transported, there is density, pressure, whatever you want. They are being transported across this system as well. So that is when we do have a viscous flow. Now in real life, are there such things as inviscid and viscous flows? Well, generally speaking, every flow in real life is actually viscous, but there are some flows that can approximate inviscid flows. So there are two parameters that we need to fulfill. So let's talk about first the Reynolds number. And if you haven't watched our video on the Reynolds number, check that out because we go through this. So rho v L on mu. So this is one formula of the Reynolds number. So what does this mean? In that video as well, I went through that this top line is the inertial forces and this bottom line is the viscous forces. So just from here, we can kind of figure, well, if we have a regular flow and the Reynolds number is incredibly high, let's say the Reynolds number is 100 million. What does this mean? It means that the inertial forces are far greater than the viscous forces because that's the only way we can get such a big number. This has to be 1 million times greater than this, obviously. That's how fractions work. So if we have a very high Reynolds number, it means the viscous forces are incredibly low, which means that we do have very little friction and viscosity is not playing much of a role. This also indicates that we don't have much thermal conduction and much diffusion. So that's one parameter. If we have a very high Reynolds number in the flow, it means that we are now approximating viscous flows. Also, we don't want flow separation. So if we have a cube, for example, now unfortunately, cubes are very bluff, which means that the flow goes over and then it will just separate. And often there will be flow separation at this leading edge as well. But definitely at the back, there'll be some kind of flow separation. This is a problem because wakes in general are very viscous phenomena. So for example, if we have a vortex and it's traveling downstream, as we keep going downstream, it will start to die out. So it'll get weaker and weaker, or we'll do a diffuse, sorry. It'll get much bigger and it'll start to die out. This is due to viscosity. So if we have a wake, a major wake, we can't really have an inviscid flow because that means the wake is not going to be breaking down properly if we were to model that as an inviscid flow. In reality, each wake is very viscous. So, and this means that any wake is going to die out over time, over length downstream. So what this means is if we want to have an inviscid flow in real life, we need a high Reynolds number, but no flow separation. So for example, if we have a quintessential airfoil, so it might even be at a small angle of attack. So it could be, 5 degrees or so, or 3 degrees, let's say. But the flow is still going over it and it's staying nice and well behaved. And it meets at the back and keeps going along. In this particular case, we don't have flow separation, so that's good. It means that viscosity is not playing much of a role in the wake here, or even over the airfoil. Also, if we have a Reynolds number very high, so let's say the free stream velocity is, 200 meters per second, or even let's say 100 meters per second, and the length of this is 100 meters, this is going to have a very high Reynolds number. So that means that we're going to be fulfilling both criteria. And we can say, okay, this situation, the flow is inviscid. Now, on the other hand, if let's say we had a free stream velocity of 0.1 meters per second and the length was 0.1 meters, it means that the Reynolds number is far lower. So this is going to now approximate more of viscous flow. And we'll see these effects of viscosity and these different parameters here. When we start to pitch an airfoil at different angles of attack, we'll see different wakes happening. I'm not going to get into it in this video. We'll have other videos on that, and we have other videos on our YouTube channel that show this, but this is just a general understanding. So let's recap what we went through today. We went through inviscid versus viscous flows. First of all, what is an inviscid flow? An inviscid flow is where we have no friction in the system, no thermal conduction, and no diffusion. Now in reality, this is not the case ever really. There's always some amount, but ideally this is what happens in an inviscid flow. What is a viscous flow? Well, a viscous flow is when we have any of these things happening. So we do have friction, we do have thermal conduction, we do have diffusion of properties. So when is a flow inviscid or when is it viscous? So a flow is inviscid when we have a very high Reynolds number, very high, and no flow separation. So no flow separation. Viscous flows is when we have a low Reynolds number and we do have flow separation. So that's in this video. Make sure to like, subscribe, and if you want to get better at CFD and or theory yourself, check out our courses and link in the description. And if you want to make your experiments 2 to 4% more accurate, which makes your CFD validation better as well, check out Atmosphere Hawk. The reason why is because the density of air changes every day by about 2 to 4%. And this is normal. This is just due to temperature changes, pressure changes, and humidity changes. And between days, weeks, months, seasons, it increases even more or changes even more by about 15% is normal. And so if you don't take into account the changes in density, you're going to have these errors in your experimental data, and that's not good. So the Atmosphere Hawk instrument we make gets that error out for you, and you can find it in the link in the description. And I'll see you in the next video. Peace out, amigos.